Long back in 1812, a Russian chemist, Kirchhoff, was studying the conversion of starch to glucose. Kirchhoff boiled the suspension of starch in water. He did not observe any change. He repeated the process by adding a few drops of concentrated acid before boiling. This time, the starch broke down to form glucose. This experiment clearly showed that acid had facilitated the reaction. Interestingly, acid did not undergo any change. The function of acid was just to increase the rate of conversion of starch to glucose. Such substances which increase the rate of the reaction but do not undergo any chemical change by themselves are called catalysts. The importance lies in the fact that only a very small quantity of it can alter the rate of the reaction. In this video, we will see in detail the effect of catalyst on the rate of reaction. As mentioned earlier, there are substances which can alter the rate of reaction, right? If the added substance increases the rate of the reaction and does not undergo any change by itself, then it is called a catalyst. For example, manganese dioxide acts as a catalyst in the decomposition of potassium chlorate. On the other hand, if the added substance reduces the rate of reaction, the substance is then called an inhibitor. For example, acetanilide can decrease the rate of decomposition of hydrogen peroxide. Hence, acetanilide acts as inhibitor in this reaction. In fact, the catalyst does not change the equilibrium constant of a reaction. Rather, it helps in attaining the equilibrium faster. That is, the catalyst can alter the rate of both forward and backward reactions, and that too to the same extent. This means the equilibrium remains the same but is reached earlier. This clearly indicates that catalyst catalyzes only the spontaneous reactions without altering the value of change in Gibbs energy. How will you explain this action of catalyst? Well, it is said that the catalyst provides an alternate pathway or reaction mechanism for the reaction. The catalytic pathway has lower activation energy compared to non-catalytic one. By Arrhenius equation, it is obvious that if the activation energy for a reaction is low, then the rate of that reaction will be high. Besides the above explanation, the action of catalyst can be explained by intermediate complex theory too. According to this theory, a catalyst can form temporary bonds with reactants. Here you can see catalyst C forms complex with one of the reactants A to result in an intermediate complex AC. This complex has transitory existence. The decomposition of this complex AC yields products and the catalyst C. This shows that catalyst is not consumed in the reaction. We may also describe the action of catalyst based on collision theory, which we will discuss in our next video. Now, I have a question for you. Tell me why finely divided catalyst is more effective in its catalytic activity than bulk metal? I can give you a hint. Think about the surface area. Now, let us summarize what we have learned.
Manorama Horizon. Learning made simple.